This is step support assignment number 2. It's actually a step 1 question from 1999. It's question number 6. Here's the question. You can have a go at it yourself if you want to first. I'm going to do part 1 first, obviously. It's talking about greatest and least values of some function between minus 10 and 10. I'm going to draw just pictures for this. Really useful in step is just to draw everything out. So let's draw an xy axis. And now the function y equals bx plus a is obviously a straight line, right? Like mx plus c. So it's a straight line, looks a bit like this, except it only looks like that if b is greater than 0, because it's a positive gradient, and a is bigger than 0. So that's this case. And we can see in between minus 10 and 10 that this line is clearly biggest at 10, in between minus 10 and 10. Of course, it gets bigger over here, but just in between minus 10 and 10, it's biggest at 10, when it's obviously b times 10 plus a, which is 10b plus a, and it's smallest at minus 10. At minus 10b plus a. So this graph has the greatest value of 10b plus a and its least at minus 10b plus a between these two values, if you're in this case. Now, what if you're in a different case? Well, let's draw a different graph for that. When this time, if we consider b to be negative, the graph will look a bit more like this. And of course, a is still positive here. But let's consider b to be negative, so we've got negative gradient this time. Again, between 10 and minus 10, this time, this graph is biggest at minus 10, like it's clearly getting bigger this way. So it's biggest at minus 10, where you have a value of minus 10b plus a, and it's smallest at 10, when you have a value of 10b plus a. So this graph has a greatest value of minus 10b plus a, and its least value at 10b plus a. That seems a bit weird, like because this is just positives and this is a negative, so how is it biggest here? Well, again, it's because b is negative, right? So the fact that b is negative in this case makes this whole thing a positive number, because minus 10 times negative is a positive, whereas this is actually the negative number here, because b is negative. So that's the case there, and we only have one more case to do, but before we do that, let's just appreciate quickly that the a doesn't actually make a difference to any of this, right? Like all the a does is move this graph up and down, but that doesn't change where its biggest value in the local between minus 10 and 10 is, and where its least value is. Like it just moves up and down and changes what that value is, but it doesn't change anything about the idea that we've got here, which is if you just move this function down 10 places, say, if you reduce a by 10 and move it down to here, it's still biggest over here, still smallest over here, and likewise here. The only other way you can change this is if you make b 0, right? So we've considered b is less than 0 and b is greater than 0, but if you consider b to be 0, then you just end up with this here. And of course, this point here is just a point a, and of course its greatest value is just a everywhere, and its least value is also just a everywhere. So kind of a trivial case, but just make sure you get them all. It does list them there for you. Part 2. So you can see that part 2 is very similar to part A, very standard in step, except they've given you a slightly more difficult function to deal with, a quadratic, rather than just a linear term. And that's basically the only difference. So let's go through this as similarly as we can. Now the first thing to say is, they've given us a nice bound on C. We know it's bigger or equal to 0. So what does that tell us? Well, if C is bigger than 0, then this is a U-shaped quadratic, right? We learned that in year 9 and 10. If C was less than 0, that would make it upside down, like an N shape. But it's bigger than 0, so it's a U shape, except it could be 0. But of course, if C is 0, then all of this term goes away, and you're just left with bx plus a, which is the case we just dealt with. So what I'm going to do for the examiner is I'm just going to make a note. If C actually is 0, just refer to my answers in part 1, because that is the correct answer. Otherwise, if I'm just going to start considering C greater than 0, right? So now I can just consider C greater than 0 because I made that note. Okay, now let's consider that then. So again, same as we did before, draw a graph. We're looking between minus 10 and 10, and we're trying to draw this graph here. Now, the problem is that when you're drawing a quadratic, these coefficients don't really help you massively as they are right now in telling you what the quadratic looks like massively. All we really know is that because C is positive, this is a U shape. So instead of working to draw the quadratic first, let's work backwards around the problem almost and think about, well, if we're thinking about greatest and least values of some quadratic between minus 10 and 10, let's instead start thinking about how that could be different. What are the different cases here? Just like the different cases for a line were just if the line goes like this or like this. Those were the two different cases with the third one here. Let's think about what the different cases are for a quadratic that would make this different. And it's a U-shaped quadratic, by the way. Well, the only defining feature of a quadratic really is its minimum point, if it's a U-shape, or its turning point. So let's put the minimum point way over to the left of the minus 10. So let's put the minimum point way over here. Now we see, in between the area that we're looking at, which is between minus 10 and 10, this graph is kind of just like the line we were looking at earlier. It's biggest over here at 10, and it's smallest over here at minus 10 in this range, right? So this is kind of just like the line we were looking at. On the other hand, if you move the minimum point all the way over to the other side of positive 10, to the right of positive 10, then you end up with it's kind of just like the line we were looking at second, the negative gradient line. It's smallest over here at x is 10, and it's biggest over here at x is minus 10, again, in the range that we're looking at. Okay, so those two cases are quite nice. I can see clearly that I'm going to be able to deal with those cases. That's fine. I'm going to have to describe the minimum point in terms of A, B, and C, but I think I can do that. And then I can put in 10 for the minimum point, minus 10 for the maximum point in this case, and vice versa in this case. Now, what other cases can I think of that would change the answer? Well, okay, so I've put the minimum point way over here first and way over here second. It would be logical to put the minimum point or the turning point of the graph somewhere in the middle. So let's put it here and think about what happens here again in the range that we're looking at. So putting the minimum point of the graph between 0 and 10. Well, now this graph is clearly smallest at the actual minimum point this time, because the minimum point is within the range we're concerned with. And where is it biggest? Well, because the minimum point is over on this side of the graph, it must be biggest over at minus 10. And we can kind of see that with my bad sketch. At 10, the graph is still negative, but at minus 10, it's really, really positive. But the reason for that is because the minimum point is over on this side, it has more time to rise over on this way. So it's going to be bigger at minus 10 than it is going to be at plus 10. So in this case, the minimum is just the minimum point, and the maximum is at minus 10. And finally, of course, the last case is when you put the minimum point over here, and then you end up with exactly the same thing backwards. The minimum point is still the minimum point, but the maximum point is over at plus 10, because again, it has more time to rise up before it gets to 10. Okay, so that's all the cases. I've talked about how the really important thing here is the turning point or the minimum point of the graph itself. So what I need to do is I need to describe the minimum point using this algebra, and then I just need to run through these four cases. So, okay, how do I describe the minimum point? I'm just thinking to myself now, I could have done this with differentiation and maybe it would have been a touch easier, but I'm going to complete the square instead. So let's put this into complete the squared form. I'm going to factorize out of C first, just from the first two terms, not the last, because you'll see why later. Just factorize it out of C from the first two terms, and then just complete the square on these two bits here. So halve this number and put it in the bracket. So half of B over C is B over 2C, and then take away B over 2C squared. Of course, that you just square each thing, which gives you this. And now I can multiply through by C again. C times that is just C times this. C times this, you cancel one of these C's below and you get this. And of course, if I had taken the C out of all three terms, that would have been an A over C. And then I just put it back in when I multiplied out. So there's no real point doing that. But this is the thing in complete the squared form. Looks a bit weird. I'm also going to swap these two terms over because I like the positives to come first. But I think this is my completed the squared form. Okay, so where is the minimum point of this graph then? Well, thinking about the minimum point is when the y coordinate is its lowest possible value. Like it turns the y coordinate is its lowest possible value at the global minimum. So for y to be at its lowest, well, let's look at this whole thing here. That's all positive. So if that's all positive or zero, for y, if I want y to be at its lowest, I want this to be all zero. Because it's something squared, so it's either positive or zero, but I want it to be zero because I want y to be as low as possible. So I want all of that thing to be zero. So let's solve that. Divide both sides by c, and I just get the same thing. Root both sides, the square root of 0 is just 0. And then, of course, that means that the minimum point is at x is minus b over 2c. And of course, I can then substitute that in to find what y is. Well, if I put minus b over 2c into there, this all becomes 0, as I wanted it to, which means y is just a minus b squared over 4. And that's my minimum point. So if I have a graph that's this expression here, I've got it here as well, then the minimum point is minus b over 2c, and then this bit. Okay, so that's good. Got it in terms of that. I could have differentiated to find that, I guess. But whatever. And if you already knew that you can just take these values for the minimum point here, that's fine, but I just want to talk about the logic a little bit there. But regardless, now I can start going into my four cases. So my first case, remember, was when the minimum point was way over here. And I talked about how essentially that means that the x coordinate of the minimum point is less than minus 10. Now I can times both sides by minus 1 to get rid of those negatives, but then remember I have to flip the inequality. So that's actually the case I'm looking at. And the minimum is when x is minus 10, and the maximum when x is 10. And I just put those numbers in, right? So the maximum is when x is 10. Just put 10 into the original equation, and you get that's your maximum point. Minimum x is minus 10, and that's your minimum point. Do that for the next case. The next case I decided was when the minimum point was way over here. That means minus b over 2c is greater than 10. Times both sides by minus 1, flip the sign, and that's actually kind of maybe the case in more simple terms. The minimum this time is when x is 10, and the maximum was when x is minus 10. We talked about that earlier. Put those numbers in, and we get our two answers for that one. Write them down nice and clearly for the examiner, and move on to your next case. When the turning point was in between 0 and 10, when the x coordinate of the turning point in between 0 and 10, again, I can times everything by minus 1 there to get this case, which is perhaps how they would prefer to see it. Now, the minimum of this is actually the minimum point, and the maximum was when x was minus 10, because again, it has more time to rise over here. So put in minus 10 to the original equation, and again, you get the same thing we've had a couple of times before. And now the minimum point is just the minimum point, which we know the y coordinate of. It's right there. So we already know that. And one more case to go. We're just looking for this thing here to be between minus 10 and 0. Again, times everything by minus 1, which I actually apparently didn't bother to do, but you get the idea. You can do that if you want to. The maximum is when x is 10 this time. Put that in. The minimum is when x is... Ooh, that should be a minus. I've messed up all kind of things with this slide. That should be a minus, as it always is, but the y-coordinate is just that, as we've seen before. Note that I never actually discussed, this is just my last point, I never actually discussed when the minimum point was plus or minus 10 or 0, but you can either add that onto your previous cases by just changing these signs to or equal to's, or you can treat those as separate cases when the minimum point is actually at minus 10 or 0 or 10. But just you do have to be careful to do it at some point. It's just I made this whole thing and then realized I didn't and couldn't be bothered to go back and do it again. You do have to consider those, either attach them to your previous cases or do them in new cases. It's completely up to you.